Okay, good morning. Now we are going to use this recording to discuss hashing. And this is Unit 4 of CS2 Data Structures and Algorithm. So in the caption, you see that we are doing hashing because we want to have efficient lookup in the table. So we have mentioned that we want to do or solve our problem efficiently, and we want to make use of whatever data structures and algorithm to help us to do things very fast. And hashing is one of these algorithm. The hash table is a data structures that we can use to help us organize the data. Right. So let's continue. We are going to go through all these topics. First of all, define what is hashing and mention how to hash. And when we say hashing, we are talking about hashing a big chunk of data into a small table, maybe, because we need to make sure that we use less memory space than the possible range of all those data. And because of that, we will have collisions. So therefore, we have to know how to resolve the collision. And in these lectures, we will introduce 4 ways of doing that, namely separate changing, linear probing, quadratic probing, and double hashing. And we also want to introduce this thing called load factor. In order for us to avoid collision, we need to know when actually the hash table is already too congested, and if you continue to hash it into this table, you are going to have a lot of collision. So therefore, we need to rehash, and the load factor will actually help us to make that decision. Okay, and then finally, we want to mention some problem, some of these collision resolution method were introduced. Right, there's primary clustering and secondary clustering. Right, so we will go through them one at a time. Right, so first of all, in data structure and programming, we are always concerned ourselves with 3 important operations. That is insertion, when we want to add things into our database, our file structures, or deletion, when someone, like for example, left the course, we want to remove the record of this person, or a company, when the staff resign, you want to remove it from the employee record. Or retrieval, we want to find those records and so that we can do some updating and so on. Right, so if we use table to represent this information and then perform the 3 operations on this table, what will be the way to do it? Right, so we can use a sorted array, and for sorted array, we know that the value was sorted. So in every time you want to insert an item into the array, you need to first of all search for the correct position to insert. And so therefore, insertion involves an ON operation. Right, so this is ON for insertion if you use sorted array. Deletion is the same thing, right? You have to, or besides finding the correct position to insert, you need to open the gap because this is array. When you open it, if you are unlucky, you are going to insert to the front, you're actually moving every item to the right one space. So that is ON. Similarly, for deletion, first of all, you have to look at the insertion point or deletion point. Of course, sorted array, we can use binary search. So that is O log n. But again, when you delete the elements, you have to move all the elements left one space. So that can involve ON operation also. Of course, just now we mentioned array retrieval means you use binary search, and that can be done in ON time. Okay, subsequently, we are going to talk about balanced BST, where the 3 operations can be done in log n time, which is much faster. But hashing promises us to get the O1 on average for all the 3 operations. So at this point, some of you might ask, and if hashing can allow us to get perform every operation, the three operation in all one time. Why are we studying all the other data structures and algorithm? So of course, there's no free lunch. When you want to achieve this O1 complexity, you must fulfill certain conditions. And that's what we are going to discuss today. Right. So we will cover the balance binary search tree subsequently. Right. Before we look at hashing, we want to mention this topics called direct addressing tables. Right, so we say that this is a simplified version of hash table. Why is it so? Let's look at it. Right. So, for example, if we are talking about the bus system in Singapore, the Singapore bus system, we know that Singapore is very small, so we might have only services number from maybe 1 to 999. So therefore, if that's the case, we can actually create a array of 1,000 items and then use the number of the bus service to be the index, and we can go directly to the entry and store the value inside there. Like for example, let's say bus number 2, we can put all this data inside here. So this one indicate that bus number 2 is actually in operation in Singapore. Right, so if you want to check whether the bus service exists in Singapore, you just use a number n, and then you just go to that location using this as an index. For example, 998, oh, you find that there's a data. So then we know that this bus service existed. If you say 999, maybe it's not there yet, so then you will see that it's not there. So if you want to introduce new bus service 999, what you do, you get all the information and use 999 to be the index and go there and store the new data. Of course, sometimes we have to remove some of the services because maybe there's a MRT station built there. This service is no longer useful, right? So of course, the company don't want to lose money, so they want to remove that bus service. So what you do, you just use n to go to that place and then just remove that record. Right. So in this case, we know that all the numbers must be integer between 0 and 999. So therefore, we can create this array with 1,000 entries to actually store all the information that we need. For example, the bus number, the distance between station, how much you have to pay, and all those information. Right? We can store it inside a table like this. Right, so to do insertion, very simple. You just use the key, the bus number to be the key, and the data will be all those information that we mentioned before, right? The station, the route, the cost, or the bus fare that you are supposed to pay, and so on. Then we just use this key to be the index and go to the table and insert this data into that particular entry. Okay, to delete the bus service or to delete this particular item, we use the bus numbers to be the key and go and delete it from the table. All right, so you just make it to become null, then in this case, it will indicate that particular entry is actually empty. To find the key, to find the record, like for example, the customer service want to reply to an email or reply to a phone call from the customer, you just make use of the key, the bus number, go there and return the record so that you can answer all the question. Right, so this is quite simple. And we are using the table directly, with the index of the key or the key as an index to go to the table. And that's why we call this direct addressing table. Okay, but there are some problem, right? Obviously, once you think about, look at it, you know, right? Key must be integer. So because we are using the index or the key to be the index to go to table, so this key must be integer between 0 and 999 in our bus example. Right. So what happens if some bus services actually indicate with an A because it won't run the whole route. So maybe from NUS, you go to a place and you stop and turn back. But if you have 10151, you go all the way to the other terminal, right? So we can have this kind of bus number, and then we can have special services. NR previously stand for Night Rider. So again, this is not integer. So this, if we have this kind of services or this kind of bus number service, we cannot use a bus number to be the key. So that will be a problem. And then the range of the keys must be small, right? So as we say already, if you have 1,000 services, bus services, we can use a table. But if we want to use, we want to do direct addressing table for student record, and the key is actually the student matrix number, and then this is impossible. The matrix number have 7 digits, and straight away you're supposed to create a table that is so big and to store all the students. That is not possible, right? So this range of keys must be small, related to the problem of not overuse the memory space, okay, wasting the memory space and so on. The key must be dense, not many gap in between the key values. So again, if you have 1,000 bus number, the gap is actually quite small because the range is actually small. So again, if you use, like for example, Singapore in identity card numbers, it will be very sparse, right? A lot of gap in between the key value. Similarly, as we said earlier, if it is student matrix numbers, it also will be many gaps in between. So how do we overcome this restriction? Meaning that we cannot use direct addressing table. What should we do? Right, so of course the answer is what we are discussing today. We use hash table, hash table, and perform hashing. Right, so we say that this is a generalization of direct addressing table to remove all those restrictions we mentioned in the previous slide. So what is a hash table? Okay, first of all, we want to introduce all this terminology. What is a hash function? What is a hash code? And what is a key? What is a home address? And so on, right? So let's first of all suppose we have a table called hash table with sign n. N is actually the number of elements that we can put inside there. Keys are part of the data that are used to identify the data, similar to the direct addressing table. Key is actually the number that we can use to identify the data, but we are not using this key directly to be the index because, as we say, there are a lot of restriction. So therefore, we have to create a hash table. Right, so the hash function. So this hash function is actually a function to compute what we call the hash code. Sometimes we call it hash value. And then by using this function produce this hash code, then we can use this hash code or hash value to be the index to go to the table. Yeah, so the function is any function that you can create. Right? Subsequently, we are going to mention what are the good or popular hash function that people use for hashing. Right, so we say that hash code is actually computed from the key using the hash function to get a number in the range. So because the size is the table size is n, so we know that we have n entry starting with index 0 all the way up to index n minus 1. Yeah, so therefore the function, the hash function, given the key, must return a value that's in this range so that we can put the record inside this hash table. Right, so whatever big numbers on the key inside here is going to be hashed into this table, right? This table of n size, size n. Okay, so we use this index, we use this hash code produced by the hash function to be the index to the table so that we can put the data inside there, or deleting the data, or actually retrieve the data for some processing. Okay, so this hash code produced or hash value produced by the hash function is called the home address of the key, right? So this this hash code produced by the or hash value produced by the hash function is called the home address of the key. What it means that every key that is put inside the hash function, the value returned is actually the home address of this particular key. right? The problem is when you do hashing, as we say, there might be collision. So when you come to this home address to actually store the value of the data inside here, you find that this actually occupied by some other people, right? So you cannot stay at home, you have to go somewhere else by using the conflict resolution method to find an empty slot for you to stay inside there. But remember this home address, this term, home address is the address of the key, and then this key put into the hash function, the value returned by the hash function. So the desirable situation that you want to achieve is that these addresses are different and spread evenly over the range so that we don't have the problem of collision. And then we say that when the two keys have the same home address or the same hash code or the same hash value, there is a collision and we have to resolve the collision. And in fact, this is a main part that we are supposed to overcome or supposed to address as compared to the direct addressing table because of this collision. Right, so what is hashing? Hashing of the system or the data, the algorithm uses a hash function, a hash table, and a conflict resolution scheme or method to implement the data, the ADT table, the table ADT. Right, then a conflict resolution scheme is the action taken to resolve the conflict between two keys that have been assigned to the same home address, to the same address by the hash function. Right, so again, when the two key after the hash function sending into the hash function and the hash function return the same home address, we have this collision, and we want to resolve this collision. What are the method to do it? Right, so first of all, we want to talk about what is a good hash function. Of course, the idea is we want to achieve O1, that's what we say at the beginning. If you want to do that, of course, the hash function shouldn't take ON or ON square or N log N to actually compute the hash function or the home address. So it must be fast. We have a good hash function should scatter the key evenly throughout the hash table, and that should result in less collision. And then you should save space. You don't want to create a big memory space for the table so that you have less collision, but that is not the good thing to do. Right? So you should need less slot inside the hash table. So of course, when we talk about good hash function, we should mention what are the bad hash function, right? So that we can avoid using those as a hash function. So for example, if we just select a digit among the given value, for example, let's say this is a telephone number and in Singapore, and if you always choose a third digit and maybe the seventh digit as a hash value, then this is going to introduce a lot of collision, right? So this is not a good hash function because every time you create collision, you have to spend time resolving the collision. So the idea is if you just, or the other way is if you just select the first three digits of Singapore home number. The idea is Singapore is divided into some region, right? So for every town or region, the first three digits are actually the same. So if you do that, every number that you receive for this particular town, you are going to get all the collision. So we should avoid that. Those are the bad hash function. Basically, we don't want to do selecting digit as the hash value. Right. So if we want to resolve collision and if we have a way to find the perfect hash function, that would be the best because a perfect hash function is actually a one-to-one mapping between keys and hash value, and there will be no collision. Right. So for example, just now we say a direct addressing table is actually a perfect hash function because they will not have any collision, right? Because we are simply using the key to be the index to the table. Right, can we produce a perfect hash function? The answer is yes. We can do that if we know all the keys beforehand, right? So if you want to create a hash function for student numbers, that's not possible because we do not know who are the students with what number are coming to the course. So it's not possible. But for example, in terms of compiler and interpreter, they can actually use a perfect hash function to search for the result words, like for example, for loop. What did I do? Right. For compiler and interpreter, we know all those keywords, like for example, for loop, while loop, print, and all those things, right? So if we know all these words already, we can actually create a perfect hash function to search for all these result words so that the compilation, the interpreting process is actually faster. So there's a website here. If you want to know more about how to do perfect hash function, you can read this video. And there is also some website, if you provide all the key that you know beforehand, they actually return you with a perfect hash function. Right. So how do you define a hash function? There are actually four ways of doing it. So we can have a uniform hash function. We can use division method. We can use multiplication methods, or we can talk about hashing of string. Right. So we'll go through this one by one. Right, so what is a uniform hash function? A uniform hash function distribute the address or the addresses uniformly into the table. But the idea is if you want to do that, the key must be uniformly distributed in the interval, right, from 0 to x. And then if that's the case, then we can make them into a hash function or hash table using this method. Right, so the idea is, first of all, we know that the key must be uniformly distributed within this interval. Right, so if that's the case, because it's within this interval, we can actually divide. This is M is actually the size of the table, right? We divide this by X, meaning that interval, and most of the time we are going to get some decimal point. Then we multiply this key to this decimal point, right? This decimal value, and then we take the lower bound or the floor of this number. So by doing that, we are actually throwing away the decimal part, and give us a key that is within this sum, this table size between 0 and n minus 1. Yeah. So this is what we call uniform hash function. The condition is that the key must be uniformly distributed. So in this case, the, the mouse is not a good, what they call, drawing tools. Right, so the key are actually uniformly distributed. So we are saying that if you do that by using this method, then you are going to get hash function or hash value that is uniformly distributed in the table also. Right, so this is good if we have this condition satisfied. Right. The second method is called division method. And we say that this method is the most popular method because it's quite very simple. Right. So the idea is map this division method map into a hash table of M slot, the same thing. This is a table sign, M. And then we just simply use this key, mode this. So mode is actually the remainder operator, right? So then you will map this value inside here. Right, so of course, this one doesn't put any constraint on the key. And of course, because of no constraint out there, that's more likely to produce a collision when we do this. And of course, we have to use some collision resolution method to overcome those collision or to resolve those collision. Right, so we say already this is the most popular method. Right, so we know that we are using the division method by looking at using the modulo operation to find the remainder after dividing by m. So what would be the good table size? We say that this table size shouldn't be multiple of 10, right? So we know that every time you divide a value by 10, the remainder is the last digit. if you divide any values by 100, the remainder is actually the last two digits and so on, right? So you say if n is actually 10 to the power of something, then when you do the hash function, the hash function you are using the popular division method, then the hash value is actually the last n digit of the key. So this is no good. It's quite similar to what we said earlier by asking by taking the first three digits of the phone number. So this no good. It's going to create a lot of collision. What about m equal to 16? Right, so we know that 16, or the other way to put it is inside the computer, all the number are represented using in the binary bit, like 0, 1, 1, and 0, and so on. So if you divide it by 16 or any power of 2, like for example, divide by 2, you are going to get the remainder equal to 0 or 1. Right, so internally, you are going to get the last binary bits. If you divide it by 4, you're going to get 2 bits. If you divide by 8, you are going to get 3 bits and so on, right? So again, this is quite similar to the power of 10. You are just getting the last few digits of the numbers. Binary number is the same thing, right? So therefore, we should not use what I call m, the table size, to be a power of 2. Right, so what about m equal to 73? So first of all, obviously, this is actually a prime number. So a prime number by doing dividing by this prime number is actually most of the time returning different value, okay, for different keys. Right, so this prime 73 is not a random number that people have studied, people have done some research and find that this number is actually very good. I think 73 is used by Java when they are trying to find the table size for their hash map, for their hashing function. So it said if to find a good table size so that we get the m, we normally want to pick a prime number so that it is also close to a power of 2. Right, so I will not answer the question why this is the case. People have done research and they find that this is actually the good number to use. So table size should be a prime number and it should be close to a power of 2 if possible. So the third method is called multiplication method. Right, so you simply multiply by a fraction a. Right, so this a is actually a fraction. You multiply this key to do it 2 times. So of course, this guy is going to produce a decimal value. You take the floor, that means you throw away the decimal part of the number, and this will return integer, right? And then this is actually a number that have the decimal part. So subtract away the integer part. This will give you the decimal part where it is 0 point something. Okay, so this will be between 0 to maybe up to 9 and so on. Right, so then you multiply this with the table size, then you take the floor again, and meaning that you throw away the decimal part, that should return the integer value. So this is what we call the multiplication method, and the golden ratio -1. What they are talking about is this a. If we can choose the golden ratio -1 for a, then it's going to be given. It will give a good spread of the hash value return. Right, so again, don't ask me why. People have done research, people have done some analysis and so on, and they find that if you use this golden ratio, it will give you a good hash value. Right, so of course, in real life, golden ratio actually appear in many of the things. So again, if you're interested, you can just key in golden ratio, and then maybe Google or ChatGPT or your DeepSeek will tell you the story about this behind this golden ratio. So it's up to you if you are interested. Right. So one problem that we encounter is previously all the method that we mentioned involve integer. Right. So then you can do division, you can do multiplication and so on. But many times we are given a string to be the key. For example, we want to talk about for shopping mall, we want to talk about a town. The value given is the name of the town, the name of the shopping mall. So how do we hash this so that we can store data related to this town or this hall into our table ADT. So how do you do it? So one way, of course, is to just simply take the ASCII value of every character inside this string and then sum them up. Okay, and then return the sum mode the table size, excuse me. Right, so this is a simple method, but we will see straight away that it's going to create problem. For example, when you want to hash this name Tan Atek, of course, if you want, you can say Tan Santek. Right, so how do you do it? You just simply take the ASCII value of all these characters. Of course, when you do this, C++ is going to convert or to do a table lookup and get all the ASCII value for you. So you do not need to go and remember what is the ASCII value for each of these character. Right, then after that, you're going to mode 11. You are going to get this. Okay, so it says that capital T is 84, small a is 97, and so on. Okay, you sum them up, you should get 825 mod 11, and you get 0. So by just simply adding all the ASCII value, Tang Ertek is going to return 0 to be the hash value. Okay, that's good, but then the problem is we can have this situation, right? So we have these three persons, Li Qingdan, Chen Letian, Chan Ting Li. Okay, so these three are three different persons. Of course, one of the things that we have to remember is that most of the time we don't want to use name of a person, or we want to create hash table that actually use the name of the person to be the key for indexing, right? So because this example show you that they are actually having collision, and also two different people can have the same name, then you have the problem. Yeah, so the idea is you look at all the name down here, their character is actually what we call anagram of each other, meaning that their characters are the same, but arranged in different order, right? So this in this case is going to return the same hash value, and then we have a lot of collision. So the problem is actually because the character is not added or calculated based on their position. So a simple analogy, for example, what is 4, 3, 2, 1, and 1, 4, 2, 3. So we see that these two number has the same digit, arranged in different order, but the value produced are different because this is 4,321 and this one is 1,423. So why is it they are different even though they have the different number? It is because each of them had different place value, right? So this one is actually 10 to the power 0. This is 10 to the power 1, 10 to the power 2, and 10 to the power 3. Right, so each one of them has different place value. So when you calculate them, it will produce different result. So the idea is very simple. If we also want to make sure that for name that consists of the same character or order in different order, then we should give each of these character a place value. And if that's the case, then we can actually produce different hash value for the same set of character arranged in different order. Right, so improve hashing of string. We shift the sum before adding the next character. So meaning that we start from the back, or we can start from the front, there's no difference. And every time before we go to the second character, we actually multiply the value, the ASCII value of the first character by some value. And then after that, you add this number to it. So when we are looking at the third character, we multiply the sum of the previous two character by a number, and then we add the third one inside there, right? So this process is quite simple. It's like this, right? So if that's the case, because they have different place value, even though they are having the same character, you are going to get different hash value. But of course, what number do you use to be the factor? So in this case, they talk about 37. So first of all, we know 37 is a prime number. And again, people have done some research and say that this 37 is actually a good number to use in order to produce a different hash value. And of course, one of the things that you mentioned, you realize is this. If every time you multiply that character by 37, the next time is actually 37 square, and the next time 37 cube, and so on, the number is going to be very big. It grow very fast. Yeah, so if that's the case, you might not have enough memory space inside, or there will be overflow in the integer representation. So the idea is sometime before you multiply the whatever sum you have already by 37, you actually mode it first before you multiply again. That will reduce the size of the or the range of the hash function or hash value that you are going to obtain. Yeah, so those are the implementation detail that you have to worry about to avoid what they call overflow problem inside the computer. Right. So we say the popular method is actually the diffusion method, but that method unavoidably is going to produce some collision. So therefore, we must talk about how to resolve collision. Right. So before that, we just want to show you that collision is actually very easily occurs, right? Very common. So there's this von Mises paradox, and sometimes we call it the birthday paradox. So what they say is, how many people must be in the room before the probability of some share the same birthday, ignoring the year and leap years or leap days and so on, will become 50%. So meaning that if you ask a group of people to tell us the birthday, what is the probability that two of them or some of them will share the same birthday, and this probability will become at least 50%. So what it means that, is the probability of having collision is actually more than 50%. So the idea is if you do a simple solution or calculation to show you, so we know that the first person, no collision, but the second person to have the same birth date as the first person is actually 364 over 365, right? Because, yeah, and then the third person is 363 and so on. So if you multiply all this and then you go and look at the collision, I mean the probability, it's actually you just need 23% to have this probability more than 0.5. So you can see that actually the percentage or the probability is actually quite high. Right. So this means that if there are 23 people in a room, the probability that some people share a birthday is actually 50.7%. So if we want to insert 23 keys into a table of 365, more than half of the time we are going to get collision. Right. So this is actually quite counterintuitive to many, but this is true. Okay. And so the collision is very likely most of the time. So we want to resolve this collision. In this lecture, we introduced four resolution method. And please remember there are four because during exam, of course, you are not going to have exam, written exam, but for NUS student, we told them there are four, but at the end, they only remember three because we discuss them more often. So these are the three that student will including the last one. Linear, quadratic, and double hashing. People will remember this and then they forget about this. So remember, there are actually four methods to resolve collision. Right, so separate changing. It is quite easy. Sometimes we call this close because it's actually the hash function, the value produced by the hash function is actually used as an index, quite similar to direct addressing. And we go there and insert the data or the record of this key into a linked list. So meaning that all the key that share the home address will be put into a linked list like this. Right? So this is one way to resolve collision. Every time you use this key, if it produce this hash value, we straight away know that it must be found inside this particular table location. Right? Right. So of course, in this case, when you want to add the value inside here, you can add it to the front. If you are, the insertion can be done by putting the value in front, or if you prefer to put it behind so that actually you have this thing called the concept, right? First in, first out. So then you might want to use a tail linked list so that you can insert here. So insertion is straight away is actually what you call O1. Okay, so what about the other two operations? You want to delete something, you have to go and search for this, right? And if you want to retrieve something, you have to go and search for this. So we know that linked list for retrieval and for searching is always ON. But the problem is that in what they call hash function or hashing, we have to restrict the number of elements that can be appear on one list. Right. So how do you do that? We use the hash. We use the load factor to actually determine the how many elements is on the list. Yeah. So by doing this, we are able to say we should not add more item into this linked list because otherwise you are going to suffer the whole n complexity. Of course, the n in this case is a whole table. But we are saying that for this one, we want to restrict the number of elements that you can put inside a linked list so that when you are doing searching, it's actually more or less constant. That's O1. Okay, so this is a quite easy or simple collision resolution method. I'm sure everybody can understand. Right, so the hash table operation is just simply insert key data. You just insert the list into this linked list. Okay, using the date using this key. Using this key, you put it into the hash function. The hash function return this hash value. You use this hash value to the table and then insert to the list. Yeah, so this is insertion. Deletion, similarly, you use a key, go to the hash table, and the go to the hash function. The hash function return this hash value, meaning the home address. You go to this entry inside the table, and in the search for that list inside the linked list and remove it. So we know that if we use the double linked list, we can do deletion in O1 time once you have located the key. And then to find the key, similarly to what we say for deletion, because deletion means you have to find the key first. Right, so we said the complexity of this operation are determined by the length of the list. So as we explained in the previous slide, we have to make sure that we know or we actually be able to restrict the length of the linked list. That will help us to get O1 in all three operations. Right, so as we say already, the load factor is actually the one that helps us to see whether we should continue to enter more value into this S function. So first of all, n, this n is actually what is the key that are already inside the hash table. Right, so the hash table can be 1000, but currently if we have only the 10 value inside there, then the load factor is actually 10 over 1000, very small, right? So again, the m is a table size, and then we define this load factor to be this. The number of items already inside the hash table over the table size, right? So a measure of how full this hash table is at the moment. If you have a 999 over 1000, it's almost full, right? Just add one more item, it become a full table, right? So the idea is for separate chaining, this data, this alpha can be actually greater than 1. Okay, because like for example, you have 100 entry inside this table, but each of them have 5 entry inside all this location. That means actually there are 500 n equal to 500, but m is actually equal to 100. So we can actually have the load factor greater than 1. But if we talk about the other three methods, load factor should always be uh, less than 1. And in fact, they are going to specify a number so that whenever this number is over this number, you should rehash everything, right? So you say that if the table size is the number of the linked list, then alpha is actually the average length of the linked list. And every time you go over this average, you should not add one more element to this list. And you have to do a rehash. right? So if that's the case, to find the value inside the hash table is actually 1 plus alpha. So 1 is actually sending this key into the hash function for it to return a hash value, and then you use this hash value to be the home address, go to the table, and then you go and look for the item inside the linked list. And that is actually the alpha. Insertion, very simple, hash function, produce a hash value, use this hash value to the table, and then insert to the front of the linked list. As we say already, if you want to insert it to the back, then you have to make a tail linked list, and then you have to just add it to the back. And then that give you the what they call a queue. If you want to do deletion, hash function produce a hash value, which is 1, and then you go and do searching, and then you go and delete the value from there. Right, so you say that notes that this alpha affects the performance of find and delete operation because you have to do searching, right? So you say that if alpha is bounded by some constant, then all these three operations are still O1. Okay, so you say if you only allow 5 elements to be in each of these linked lists, then it's actually a constant value. Open addressing. So separate changing is a closed addressing, similar to the what they call direct addressing table, because the key is a fix, right? Every time you produce this hash value, it is actually go to one location. You do not need to look for alternative location to store this thing. So we say that when the hash function produce this hash value and the key is open, meaning that you have to look for a different location when the home address is actually occupied. If that's the case, we have this thing called open addressing system. Right, so hash the item are in a single array. Hash code give the home address. Collision is resolved by checking multiple positions, and each check is actually called a probe. Right, so the value returned by the hash function, you go to the using this as an index to go to the table, and you find that this position is occupied by someone else. You have to, so this is the first probe. Every time you go to the home address, it's called the first probe. And then if it is occupied, you go to the second place using one of the resolution method, and you go to the second place, it's called the second probe. Okay, so sometimes we also call this the probe sequence. The first, the home address, the second place where you visit, the third place that you visit. This whole thing is called the probe sequence. Okay. So, right. So the first method, open addressing resolution method is called linear probing. Right. So we take some example. You should see what they call the meaning. Right. So you say that in linear probing, where there is a collision, we scan forward to the next empty slot until the end. If you still cannot find, you might have to wrap around to the 0 again and continue to find the last slot, okay, or the empty slot. So for example, if we want to do something, so this is a table that have only 7 value, right? So m is equal to 7. So and we note that 7 is actually a prime number, very close to 2 to the 3, right? 2 to the power 3. So let's say we have this table. And then now we want to hash 18. So 18 mod 7, because table size is 7, mod 7 is equal to 4. So we just insert 18 into location 4. And then next one, we want to insert 14. 14 mod 7 is equal to 0. You go to 0 and it is empty, so you just put it there. Okay. So now I want to do 21. So hash 21 with 7, you get 0 also. So we straight away find that the home address of 21 is occupied by 14, right? So we have to look for the next slot, which is actually 1. So this is linear, right? Just go down. And so therefore, you see that we put 21 inside here, right? Simple. So hash 1. So even though the home address of 1 is actually, home address of 21 was supposed to be 0, but because of collision, it go to 1. It occupy others people home address. So when 1 come, you cannot go into 1, you have to go to 2, right? So the next empty slot. So that is what we call linear probing. The idea is actually quite simple. What happens if we want to insert 35? So 35 mod 7 is 0. So you go to 20, go to 1, go to 2, and then you find that the 3 is empty. So you put it inside there. So straight away you notice something, right? All the key are actually clustered together. Okay, let's see what is supposed to say down here. So if you want to find, so before we say that, you want to find 35, you have to do the hash value, which is 0. You go to 0, you find that it is not the value that you are looking for. You go to the next slot to find until you go to the third, after 4 prods, right? So this is first prod, second prods, third prods, and then this is fourth prods, right? After fourth prods, you find that 35 is inside there and then return true. Okay, and so just now we say already, the prod sequence is actually 0, 1, 2, 3, okay, not 14, 21, 1, and 35. The prod sequence is actually the slot, the index of the slot. So in this case, the prod sequence is 0, 1, 2, 3. Yeah. Okay, so you have to look for 8. You find that K mod 7 is actually 8 mod 7 is equal to 1. So you go all the way until you find an empty slot. When you see an empty slot, it means that 8 is not found. Okay, 8 is not inside the table. How about deletion? So you delete 21. This one is simple. You just go to the 0. It's not 21. You go to 1. You found it. And then you delete it. Okay. So can we delete it just by removing it? For example, previously when we say the direct addressing table, we just put null inside there. But by doing that, will it cause any problem? Let's see. Right, so now I want to find 35. So just now we said that to find the value, you go and go linearly until you find an empty slot. And then if you find an empty slot, that means the value is not there, right? But in this case, you can see that when you go to uh, position 1, it is an empty slot, and you are going to report that 35 is not there. But we know that 35 is actually further down in the table. So in this case, this is incorrect. So why you have this problem? It is because when you do deletion, you actually just simply put down inside the location, and that creates this problem. So how do we overcome this problem? Okay, so we do something called lazy deletion. So in computer science, if you are lazy, you have to do more works. What does it mean? So we cannot simply just remove the value because it can affect fine. So what we have to do is we have to create another table, right? And then this table is called the state table for the value for the location for the tables, right? So in this case, this table inside there, or you can use the same table, but you add in one more indicator to say that what they call this slot is either occupied or it was occupied and then deleted, or this is an empty slot, meaning that nobody used it before, right? So in this case, you have to add in one more status inside your table. So when the value is removed from linear plot hash table, you just mark the slot to be deleted, which means previously it was occupied, but now it is deleted. So you cannot just simply empty the slot. Okay, so need to use this state array that is the same sign as a hash table, or as I say, if you use a record inside this table, inside the record there's a status to indicate whether this slot is actually having which stage currently. Right, so we revisit. So in this case, first of all, we delete 21. Right, so this is marked as deleted now. Right, so now you want to find 35. So again, you go to 0 and you go to 1, and 1 is actually marked as deleted. You skip over it to go to slot 2 and then go to slot 3 and you find 35 down there. Right, so this overcomes the problem created by deletion by doing some work. So now we can insert 15. So the idea is if we only allow unique number inside there, Then when you are asking to insert some number, we make it to become a precondition for the user using this hash table to ensure that there's no duplicate value inside there. If that's the case, anytime you find an empty slot, you can straight away put the value inside there. But if you are going to allow what they call duplicated or actually before you delete, you cannot add another value. And then if that's the case, every time you encounter an empty slot, you can put it there. But the problem is sometimes you did not know and we didn't make it to become a precondition, and then the user actually asks us to insert a value which is already existing inside the table. Then we have to be very careful, because every time you find an empty slot doesn't mean this value is not there. You have to look for the whole value, the value inside the table until you are certain that this value is not inside the table yet, and you go back to the empty slot and put it inside there. Okay, and of course, once you put it inside there, you have to change the status to become occupied. Yeah. Right, so performance of a hash table, we say that for separate changing, it is O1, very good, because the number of elements inside there is still 0, so therefore we can just in O1 we can actually insert the thing inside there. But if you have some value inside there already, load factor is equal to 0.5. Linear probing will take 1.17 time to actually achieve the or do the tree operation, whereas for separate changing is actually 1.13. But you can see that if it is 0.95, meaning that the table is almost full, and if you still do linear probing, the number of probes is going to increase to 10.5 and so on, right? So you say for successful search, the number of probes is actually this. Okay, so on average, so one is to send the value into the hash function to return the hash value, and then this is actually the part where you are doing searching, you are and so on, right? So for separate changing, we say that it is like 1 plus alpha over 2. Right. Then the problem of linear probing. So we can see that by adding all those things that we have done previously, we see that all the numbers are clustered to the home address of some numbers, right? Because even though some of the value, like for example 15, okay, 15 is inserted later. For example, 1. The home address of 1 is actually 1, but it actually put into 2, right? So all these numbers are clustered together. A cluster is a collection of consecutive occupied slots. Okay, and the cluster that cover the home address of a key is called the primary cluster, right? So all these are cluster down here is actually near to, like for example, for 1. So this cluster 14, 15, 1, 35, 18 are cluster around the home address 2, right? So this linear probing can create large primary clusters that will increase the running time for the tree operation, find, insert, and delete. So this is a problem, because if the cluster grow too big, the tree operation is going to become ON instead of O1. Right, so this is called the primary clustering, and we have to overcome this problem. And one of the simple thing to do is don't use linear probing. Right, so in some time we can actually improve linear probing by a little bit, meaning that instead of adding 1, adding 2, adding 3, which is actually linear, we can actually multiply it by a number so that it actually creates some gap between the first probe and the second probes, right? Something like this. Okay, so this is one way to do it, but still it actually cluster along this path, right? 1D, 2D, 3Ds, and so on. Okay, so where this D is just a constant integer called prime with M. And again, prime number actually help us to produce or reduce the number of collision. Right, the second way of overcome the primary clustering problem introduced by linear probing is called quadratic probing. Right, so instead of using just the number multiplied by D, So this is the the step, right? So go back to C. Yeah, so instead of just multiply the same constant to 1 to 2 to 3, still cluster along the path, right, of the gap that we actually create. So instead of doing that, we say we jump, instead of 1, 2, 3, or 1 times D, 2 times D, 3 times D, we actually jump with a gap of 1 square, 2 square, 3 square. So there's no constant gap in between the two keys that have the same home address. Right, so this is what we call quadratic probing. So the question is this the best way to resolve the collision, I mean the linear probing clustering problem we want to see, okay? So first of all, we try to see how we can understand quadratic probing by looking at some example, right? So similarly, like for example, I want to hash 3, so equal to 3, right? And then hash 18 is actually equal to 4. So the 18 is inserted to here, but how come the 3 is not there? So 3 will be here, 3 will be here. Yeah, a wrong sequence. Okay, so in this case, if we hash 38, 38 mod 7 is equal to 3, right? So you come to your home address, you occupied by somebody else. So this is actually collision. So we add 1 square, right? We add 1 square from the home address, you get 4, right? So that is actually the collision again. So we add 2 square. So remember, this is again another problem that most of the students encounter or uh, have done. You have to go back to the home address and add 2 square. So meaning that it's from, you count from here, 1, 2, 3, 4. Okay, so you have to put the 38 inside here. So student always do this. Because you are already here, you find that it is there's a collision, they add 4 from here. So you say 1, 2, 3, 4, and they put 38 down here. This is wrong. Okay, so remember, if we go back again, right, so it's actually the home address, add 1, the home address, add 2 square, the home address, add 3 square, not from where you stop in the previous probe. Okay, so remember this. Otherwise, you will get your answer wrong. Okay, right. So you go here, you put 38 down there. Now, so the idea is I can quadratic probing always find the empty slot. So you say that if you insert 12 inside the previous example, followed by trying to insert 10. So and then you say what happened. So let's go back there. So you say first of all insert 12. 12 mod 7 is equal to 5. Right? So you put 12 inside here. You put 12 inside here. Then you try to insert 10. 10 mod 7 is equal to 3. So this is home address. Occupy, you add 1. You occupy, you add 4. Come back to here, add 4. 1, 2, 3, 4. You come to here. Occupy, you add 9 from the home address. 1, 2, 3, 4, 5, 6, 7, 8, 9. Occupy. Right? Then you go back and add 9. The next one is 16, right? So you go here, you add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, it's occupied. So you go back to the home address, you add 25. So you can continue to do it, or maybe when I'm doing this, you go for a cup of coffee and then you come back. So by the time you come back, you're going to find that I haven't finished. Okay, it is because I cannot find the empty slot no matter how many times I add the square of certain number. So this is a problem, right? And how come we have this problem? Again, people have done some what they call research, and they say that if alpha is less than 0.5, which is the load factor, if the load factor is less than 0.5, that means the table is less than half full, right? And M is prime, then they can always find the empty slot. But if the load factor is greater than 0.5, then it cannot be guaranteed. Even if there are still empty slot available, you might not be able to find. So therefore, we say that if you use quadratic probing, the worst case 50% of the hash table is actually wasted, because every time you load factor is get more than 0.5 or more than 50% occupied, you are going to have to do rehash. And rehash is actually a very expensive exercise. Okay, first of all, you have to create a table, maybe double the size plus one, or make it to become a prime number of the original table. And then you have to take out every elements that already inside the original table and hash it into the new table. Why do you need to do that? Because now the table size is different. If you don't rehash it, you might not be able to find those values inside the new table. Think about it. I'm sure you can understand. Right, and also quadratic probing also introduced what we call the secondary clustering, quite similar to what we say already. For linear probing, if you just multiply by D, there's a consistent sequence that you have to probe. 1 plus D, 2 plus D, 3 plus D. So there's a sequence where all these elements are going inside there. Similarly, for quadratic probing, you are going to probe in this sequence, right? Plus 1, plus 4, plus 9, plus 16, and so on. So again, this is going to form a cluster. I mean, that means a list that you have to probe before you can find the value that you want and so on. Right, so this is called the secondary clustering, and are formed because of the same pattern that we have all the time for all the keys. Right, so again, to resolve secondary clustering totally, one way is not to use quadratic probing. Okay, because we say that beside the secondary clustering problem, there's still a major problem that you might not be able to find the empty slot if the load factor is actually greater than 0.5. So eventually we come to this double hashing. Okay, for all the other methods, we have all these primary clustering, secondary clustering. For quadratic probing, we still have the problem of not finding the empty slot. So people introduced this thing called double hashing. Right, so you say to resolve the secondary clustering problem, we break the probing pattern. Instead of 1, 4, 9, 16, and so on, we actually introduce the second hash function, because two different key going into a hash function is going to produce different hash value. So for each of these key, we use the secondary hash function to produce a hash value to indicate how far is a gap to jump. Right, so that is the idea. So previously we see that this is for linear probing is actually the hash key plus 1 plus 2 plus 3, right? So this is linear. For probe, what they call quadratic probing, you add 1, you add 4, you add 9, 2 square, 3 square, and so on. So, but this become a consistent pattern. So what we are supposed to do down here is you introduce a secondary hash function. So the key into going into here will give you a different gap that you are supposed to jump. And then if after you jump the first probe, if you go to the second probe, this is still occupied, you just multiply the hash function, the hash value produced by the secondary hash function by 2, by 3, and so on. Yeah. So why this is not going to be clustered, because different key coming into the same secondary hash function would produce a different result. So actually the jump is actually not following the same path. So we say that the hash2 function is called the secondary hash function. And then it defines the step measure from the home to use in proving the free slot when the collision occurs. Right, so take an example again. So let's say we have already put in 14 and 18. Now we want to hash 21. So 21 mod 7 is equal to 0. So it's occupied. Instead of say jump 1 in linear and quadratic probing, you actually put 21 into the secondary hash function here. Okay, so this is a secondary hash function. So 21 mod 5 is equal to 1. So this will indicate that we are supposed to put the value 21 in the next slot on the home address. Okay, we put it there. Okay, so now we want the hash 4. 4, the mod 7 is actually equal to 4. And then put 4 into the secondary hash function, the value is equal to 4. So that's why we are jumping 4 from here, right? 1, 2, 3, 4. And then it is still occupied, you jump again. 1, 2, 3, 4. And you find the empty slot and you put it there. Yeah, and you put the 4 there. Okay, so it looks fine, it looks good, and whether there are going to be problem. So every time we introduce a new method, it always introduce some new problem, right? So whether double hashing is totally good, let's see. Okay, so what happened if I want to hash 35? 35 mod 7 using the original hash function, it give you 0. And then you put 35 into the secondary hash function, it's also 0. So what is happening? This 0 or this secondary hash function is supposed to produce the value for you to jump, the gap that you are supposed to jump. Right, so because it's 0, you are going to do this all the time, all the time, all the time. And again, you can go and have a cup of coffee before I come back. I'm still doing this, right? So in this case, what it indicate that is that we cannot, the secondary hash function cannot produce a value of 0, right? Cannot produce a value of 0. Otherwise, you have this infinite loop, right? In Singapore, the Malay word for this is hentak kaki, which means that you just step on the, you do on the spot stepping, right? Just step on there, but you are not moving anywhere. Right, so to overcome this problem, meaning that we have to find a hash function that is going to guarantee with a non-zero hash function, hash value. So how do you do it? You can do something like this. Okay, so this is what we described. Okay, we can do something like this using the key and then get the value. And we say that this value could be 0, and then we just add 1 to it. Okay, and then or otherwise we can actually use S, which is actually the table size in this case, S, and then we just move by using the secondary hash function, we get a value, and then this S, sorry, this is not the table size, just another value. Okay, and if this S minus 0, you get S. If this S minus 1, you get S minus 1. So definitely this is going to produce a non-zero value, right? Because it's subtracting the remainder, right? So the size of the table size has to be a prime number. Then when you declare this, we say that this S and P must be co-prime. Okay, normally we say that they are co-prime means they don't have a common factor between the two, right? So again, people have studied and say that this is the best way to find you the empty slot the faster, right? But both of them, S need not be prime number as long as they are co-prime. So that S and P don't have the common factors. Right, so if hash value is equal to 1, then this is then become the linear probing. Right, if hash value become D, and D is a constant between I mean greater than 1, then it is the same as modifying the linear probing. Okay, so good collision resolution method should also have this property or characteristic. So the small cluster size, we don't want linear probing because it creates a linear clustering. We don't want to use uh, quadratic probing because it produces secondary clustering. And of course, it must always find the empty slot if it exists, right? So quadratic probing is no good. Linear probing still can find the empty slot because it just go down to next slot until you find the empty slot. Right, so the idea is given two probe sequence, when two keys collide, so we want to make sure that they produce two different probe sequence. So therefore, there's no clustering. And then, of course, again, you have to be fast. So what do you mean by rehash? I have mentioned this many times. So in quadratic probing, we say that if the load factor is already greater than 0.5, you have to rehash, right? So when the table is getting full, even if there are other, for other resolution method, linear or double, if we have this table size and we have already put in maybe just table size minus one element, the next one you put inside definitely is a collision, unless you are so lucky that you find the empty slot straight away. So if that's the case, when the table size grow too big, we have to actually rehash. Otherwise, the operation will become very slow. Right. So we say that for quadratic probing, the insertion might fail because we cannot find the empty slot when the load factor is more than half. So the refresh operation is this. So you build another table that is almost twice as the original table, and then make sure that the table size is actually a prime number close to a 2 to the power something. And then we scan the original table. For each of the key inside there, you compute using the new hash function and insert this data into the new table. And then you delete the original table. Of course, if you don't care about this leakage of memory space, you do not need to do the deletion. But for good practice, we normally delete it from the original table. Okay, and then the load factor is used to decide what time to rehash. Open addressing 0.5. Some of the system do 0.75. Okay, for close addressing, we say 1. Okay, so in summary, this chapter or these lectures, we discuss how to hash. We look at the criteria for good hash function, and then we look at how to resolve collision. Remember again, there are 4 resolution methods. Okay, separate changing, linear probing, quadratic probing, double hashing, and then we look at the problem on deletion. So meaning that we have to do lazy deletion, otherwise we might interpret wrongly when we are doing searching. And then we talk about how to overcome primary clustering and second clustering. So I hope you can understand what we discussed. Concepts are quite simple actually. If not, please go through the lecture again to get a better understanding. Right, so we don't care about all those. Right, thank you for viewing. We will look at the next lecture some other time.